section 2.1, tangent lines and velocities, where we're headed next. And as we take a look at this, we've actually talked already a little bit about what secant lines and tangent lines are. We did it on the very first day of class. Do you remember the difference between a secant line and a tangent line? Good. So I'll do this as my curve. So, Micaiah, tell me again what you were saying.
You said the secant line cuts 2 points.
Right. So a secant line goes through 2 points on the curve, so it might cut through the graph something like this, right? And then so how is that different than a tangent line?
The tangent line touches 1.
Right. And we actually can pick that point. Let me just pick a point right now to talk about so we can discuss it in this way. So there's a point. It's 1 point. I have to draw a line so that it touches at only that point. That was not so straight. Let's try that again. That's better. So that it touches at only that point, and at least at a nearby area, it doesn't go through the curve again. Now, if this graph actually did something like this on the end where it went back up, it would go through the curve again, but that's neither here nor there. Okay, we're talking about in a nearby area to the point that it doesn't go through the curve again. So taking a look at this idea, we actually can talk about the slope of those lines, no matter which line we're actually looking at. We're going to talk about the slope of the secant line first. So if we have the secant line and we have the points A and F of A, or A, F of A, excuse me. So let's say right here that this is A, and then the Y value right here that it corresponds to is F of A. Sorry, I can't write small enough to make that really make sense, but is everybody good with what I'm talking about here? That's the Y value. You know what, let me do it this way. I have an idea. This might make it clearer. This point right here is A, F of A. And then our second point over here is some value A plus H, and then F of A plus H. That is that the distance between these two values is H. So something just a little bit bigger. Or it could be a lot bigger, but the idea being that it's bigger. Then if we want to find slope, we actually know that we take the Y value. So we're going to take the second Y value, F of A plus H. We're going to subtract the first Y value, F of A. And then we're going to divide by that second X value, A plus H, minus the first X value, which is A. And then if you notice, the denominator simplifies pretty quickly, right, to simply H. And that should make sense, because this is saying I want the difference in two Y values divided by the difference in the X values. And when we set up the difference in the X values, we set them up so that the difference in green on the screen there is actually H. Is everybody good with that? Well, what happens when we're working on, and I'm about to switch to the next slide, when we're working on a tangent line, is we want those 2 points from the secant line to simply get really close together. If those points were really, really close together, they would be getting awfully close to the same 1 point, the point that I've called the tangent point there, right? So if we're taking a look at the definition of the slope of the tangent line, we have that same F of A plus H minus F of A over H. That part's the same. The different part is this at the beginning. There's a limit, right? And the limit is that H approaches 0. So back in my picture, the limit issue is that we're actually letting those values get really close together. The difference between the A and the A plus H value is becoming nothing. They're approaching the same point. Okay, so somebody answer for me real quick. What's the difference between the slope of the secant line and the slope of the tangent line? There's only one difference. What is it? Tangent has a limit, right? The information, the value, it's called a difference quotient. You may have seen it in algebra. This piece right here is the same. The only difference is that when you're working with limits, when you're working with tangents, you have a limit that you're approaching. So I want to show you how we work with that information and do an example with it. All right, so let's take an example. We have a function. Our function is g of x. I guess I should have said f of x so these match. Let me do that just so that they match. This is f of x. F of x is 6 minus x squared. And we want to find the equation of the tangent line at a equal 1. Okay? So we're gonna graph it when we're done to actually show that it really makes sense what we've graphed and it works. Okay? So what we're actually asked to find is we're asked to find the tangent line. But in order to find the tangent line, I first need to find the slope of it. I guess I shouldn't say first, but at some point I have to find the slope of it. So taking a look at the tangent line, the way that I do that is I find the limit as h approaches 0 of f of a, which is 1, plus h, minus f of a, again, which is f of 1, over h. There's another way to do this. Some of you might have seen the other way before, and I'll mention it when I get done with showing you this way, okay? But this actually matches up, it mirrors what's over here. I have f of a, which is 1, plus h, minus f of a, which is 1, over the h. Everybody good with that? Okay. Now, in taking a look at this, we actually have to find out what is f of 1 plus h and what is f of 1. And we can do that based on this function for f. So I have the limit as h approaches 0, which we're going to keep writing just like in chapter 1 when we worked with limits until we actually plug in 0 for h. And why can't we do that yet? Yeah, I get a 0 in the denominator, right? So somehow, as I'm simplifying this, my goal is to get that h in the denominator to cancel out somehow in the numerator so that there is no more h in the denominator. That is the end result here. That's our game plan. Get the h to cancel out. So I actually have to find, let me start with the f of 1. How do I find f of 1? I plug in 1 for x. You guys have done that before, right? And we've seen that before in this class too, but you've done that in several math classes before. F of 1 simply means plug in 1 for x. So over here that would mean that I'd have 6 minus 1 squared, and the squared is on the 1. Okay, so that's the second half of this. Let me draw a red line through here so that I'm not losing you, because I'm about to lose myself. All right, this other piece right here says f of 1 plus h. What does that mean? Exactly. So wherever I have an x, I'm going to put a 1 plus h. So the 6 remains. The x becomes 1 plus h, and it's squared. And this is all then divided by h. Okay, so what do you remember when you have 1 plus h squared? What has to happen? You have to distribute, and you can't just distribute the square over, right? No. We have to do something where you're foiling, where we actually write it as the two separate factors, which is what you're thinking of, Brooks. Write it as the two separate factors and then multiply it out. So I'm going to cut to the chase on doing that. If you're not remembering how that foils out, that foils out as 1 plus h plus, I'm sorry, there's a 2 missing. Maybe that didn't look right. 1 plus 2h plus h squared. And then on the second part over here, 1 squared is 1, and then I've got 6 minus 1, so this is minus 5, right? Okay. All over h. And you notice as I'm writing, I'm still writing limit h goes to 0 because I have not taken care of that yet. All right, so let's distribute that negative through. So I have 6 minus 1 minus 2h minus h squared. I still have that minus 5 at the end, and it's all over h. So somebody tell me some kind of simplification that you see.
6 minus 1.
All right, and I've got a minus 1 here too, don't I? So 6 minus 1 here is 5, and then I've got minus 5. So all of those constants add to 0, don't they? And they better, because if they don't, we're going to have a problem dividing by h. we need the h to cancel out. And if I have anything in the numerator that doesn't have an h in it, it can't cancel out. That's not possible. So the fact that we got this h here in the 2h term and the h here in this h squared term, that's not an accident. That will always happen if you've done it correctly. You will always end up with h in every term that's still left in the numerator. Now I want to show you one more step that is, I don't want to say it's absolutely crucial to doing, but it's easy to forget when you're seeing certain values. So I'm going to show it to you. What I do in the numerator then is I'm going to factor an h out. That leaves me with negative 2h minus, not 2h, negative 2 minus h all over the same h. Right? So negative 2h became the h on the outside. The h squared took 1h on the outside. The reason I mention that is because I want to make sure that when you reduce this, you understand that that h actually comes out of every term, not just one of the terms on top or something like that. It actually comes out of all of those terms. So what I end up with here then is the limit as h goes to 0 of negative 2 minus h. Can I plug h equals 0 in now? You betcha. What do I get? Negative 2. And what in the world did we just find? The slope of the tangent line. Very good. So this is m tangent. That's the way your book is notating. That's the slope of the tangent line. Now, I wasn't asked exactly to find the slope of the tangent line. What was I asked to find? The equation of the tangent line. So how do you get an equation of a line? That's one of them. Or you could use point slope. You can do it from either perspective. You can use either one of these. But if you'll notice that we don't have all the pieces of either one right now. We have m. We just found m is negative 2. Oh, I guess I should have put that in. This is x minus x1. I actually have x1. Sorry, I was already writing that in. x1 is the number 1, right? Because that's the a value I'm doing this at. The a is equal to 1 over here. Whoops. So that's actually my x1. But I don't have y1. How could I get it? Plug it in. In fact, we already did that, didn't we? We did. We actually found that f of 1 was 5. So we do have the 0.15. And because we have all the details to put it in, I'm going to use this form over here. You could use mx plus b and then solve for b. That would be fine as well. But I know that y1's 5. I know that m is negative 2. And I know that x is 1. So I've got y minus 5 equals negative 2 times x minus 1. And if we simplify this a little, we get negative 2x plus 7. The only calculus part of that was the limiting process that you did. Everything else was actually algebra. So this is the answer to the question, but it asked us to do one other thing. What did it ask us to do? Graph it. So let me show you how you do that. Grab your calculator out for me. In your calculator, I want you to put the original equation, 6 minus x squared, okay, into y1. And into y2, I want you to put this new equation that you just found, negative 2x plus 7. You can do a standard zoom window. That's a zoom 6, which is a 10 by 10 window. Now what you're doing on this is really more than anything a check step. It's you verifying that what you found makes sense. That's not perfect, but let me see if I can. That's closer. My x value over here was 1. Apparently that was at a y value of 5, right? And does it look to you like there's a line going through that? Yeah, mine did too, which is really good to feel like we actually found something reasonable, right? Now, it's hard to verify for sure that that's the tangent line exactly, but it's reasonable when we look at it, which is the point of doing the looking at it part, is does this actually look reasonable? Is everybody good with that? Okay, let me make one comment back here. There's one other way to do this than what I did. And I'm going to do an example of this other way here in just a minute. I actually chose to put in the 1 for the A's at the very beginning, right? The other thing that you can do is you can just leave it as A and do all the work with A involved, and that may sort of seem to you like that seems harder, and in reality it's usually easier. And then you plug in the value for A at the end. And I bring that up because I'm going to show you a case where it's easier. So we're going to talk about velocity next. This is instantaneous velocity. So we're going to take a function that actually has a representation for what it means. S of t is a position equation. So it talks about where a object is at a given point in time. So you want to think about, like, if somebody calls you on the phone and they say, "Where are you?" when you're driving home, and you say, "I'm at exit such and such," or "I'm on the highway at this particular point on the highway," or "I just passed that Love's across the street." That's the position that you're talking about, okay? Now, you may be camped out there in your car and not moving. They didn't ask you that. They just asked you where you were. So that's position. What we're actually trying to find is how fast you're moving at that point in time, and that's velocity. So instantaneous velocity is actually similar to speed, and you can see that down at the bottom. The way that they are related is that speed is the absolute value of velocity. So if you sort of imagined that you were talking about how fast you're going, and you just passed that Love's, but you passed it going the wrong direction, probably not helpful if somebody's waiting for you back the other way, right? For you to say, "I'm past the Love's and I'm going 75 miles an hour, but in the wrong direction." Okay, so speed actually takes no consideration of the direction. Velocity will. And so take a look at this. We've got this limit as h approaches 0 of s of a plus h minus s of a over what simplifies to h over here. That should look vastly familiar, right? That's the exact same thing we just did. It just has a different application. So when we're talking about a slope of a tangent line, or we're talking about instantaneous velocity, we're talking about the exact same thing. Okay? That's worth writing something down to yourself, that those two phrases mean the same thing. They mean do this limiting process and do this difference, it's called a difference quotient with the limit value in front of it. They mean the same thing. So let's take a look at one, and I'm going to talk about this one. And to some extent, I want to talk about it as to why I'm going to put the A in there and leave it. Notice right here, I have been given two different A values, right? I'm wanting to find my velocity, kind of like my speed, at two different points in time, right? And the problem is that if I put in A equal 1 and do all the work, then I'm going to have to redo all the work with A equal 2 in there. I don't know about you, but I'd rather do the work one time. So I'm going to show you how to do that with the A in there, and you can think about whether or not it makes sense to always do it or sometimes do it or whatever. So we're looking for the tangent line, or in this case, they're actually referring to it as the velocity at a particular point in time, A. And I'm going to leave it generally as A. And we want the limit as h approaches 0 of s of a plus h minus s of a over h. That's just, we start there all the time. That's the definition. That's how we find it. So this is a limit as h approaches 0. All right, so here's that s of a plus h. What does s of a plus h tell me to do? Okay, let me do this one then. How would I find s of a? Plug in a in place of x, right? So it doesn't look like it's very exciting on this one, right? But I'm going to take the 2. I'm going to put in the a in the place of the x as the second function. Right, so s of a right here is the 2 over a plus 1. So if s of a means plug in a in place of x, what does s of a plus h mean? In place of x, right? So it looks like it's sounding like there's some sort of an addition going on, but really all that happens is that the piece that gets plugged in is different. That's all it is. So instead of having 2 over a plus 1. I have 2 over a plus h. Plus 1, yes. Sorry, my plus is not working out very well. I'm trying to write too small. Okay, I think that that's all right. So think back for a minute to the last problem. What's the overall goal here as we're working through this? Cancel out that h, right? We don't want that h in that denominator because I can't plug 0 in as long as it's there. So what are we going to do on top? Because this one is not quite as simple or clean as the last one. Any thoughts?
Do you get a common denominator?
That's right. Very good, Hannah. I have two fractions. And the way that I'm going to be able to change fractions is to get a common denominator between them. So I need to get a common denominator between them. And as you can imagine, they don't really look like there's any way to do that with like factoring or anything like that. And there isn't. So in order to get a common denominator, the common denominator is simply going to be the two denominators multiplied. Yeah. So I'm going to take the first numerator and multiply it by the second denominator. And I'm going to take the second numerator and multiply it by the first denominator. And then I'm going to multiply the two denominators by one another. And the reality is I'm going to draw this in and then I'm going to erase what I did. This is all over h, right? I don't really want it written like this because I've got a double fraction going on. So I'm going to write it instead as times 1 over h. So division by h is the same as multiplication by its reciprocal, 1 over h. So in essence, basically, this h is actually simply going to be part of this denominator. That's missing. All right, simplifying that first numerator. Well, I've got 2a plus 2 minus 2a minus 2h minus 2 all over a plus h plus 1 times a plus h, I'm sorry, a plus 1, get the right thing there, and then times the h on the end. What simplifies? The 2a's cancel, and the 2's cancel, leaving me with negative 2h on top. So I've still got the limit as h approaches 0. I've got negative 2h on top. I've got a plus h plus 1 times a plus 1 times h on bottom. Does everything in that numerator now have an h in it? You betcha, which means I can reduce it, correct? So now this h on this numerator, because this is all factored now. I don't have any addition that's outside of factors, right? This numerator has an h in it. This denominator has a factor of h in it. So I can reduce the h's in the denominator with the h's in the numerator, which simply leaves me with the limit as h approaches 0 of negative 2 over a plus h plus 1 times a plus 1. All right, can I plug in 0 for h? What do I get? Excellent. So what I actually end up getting is that the velocity equation, v of a, is negative 2 over a plus 1 squared. And that's really nice because now I can actually find, okay, what then is the velocity when a is 1? And I'll use this equation. I mean, that's the whole process we just did, is we found an equation for velocity by plugging in 1 into this equation. So I would have negative 2 over 1 plus 1 squared. And what do I get? What did I get? Negative 1/2? Yeah? Is it right? 1/2? Because I'm going to get a 4 on bottom? Yeah. So this is negative 1/2. Sorry, I'm running out of space. And then we can also do v of 2. And we can do them so quickly back to back because we found the general equation first. So v of 2 is doing the same thing. I now have negative 2 over 2 plus 1 squared. What's that give me? This is still, the 2 still on top, so I've got negative 2 still on top, but what's the bottom become? 9, so this one won't reduce because I've got a negative 2 on top. Remember that 2 on top is a part of the general equation for velocity. It's not coming from the A or that I was given. So it's negative 2/9. So these are the two answers that I get for the two different velocities. That's a 9 down there. It doesn't look like it, but my screen won't let me write any lower, I don't think. No, pretend. That's negative 2 over 9. Okay, it's not an A. All right, we have time for the one last one, and then we'll finish next time. I realize that your graph doesn't, I mean, it looks just like this pretty much, right? It's missing some points simply because of the way that I have to do things on PowerPoint to make this work. So I want you to do this with me first and put in some points nearby at least to what I've got so that we've got a similar image going on. So go ahead and do a point at, are they written in there in the right order of what yours are?
No.
That's what I thought. I was like, I don't remember them being there. Fabulous. All right, I'll fix that in just a second. Let's put in the dots for them first. So the first one's going to be really close to the top of that curve. The second one's at the top of the curve. The third one is somewhere nearby that x-axis point. And then the other one's over here. And let me relabel with what yours has. This has A, because they're in order, aren't they? Copy, paste, I tell you what. All right, oh, that one's D. Okay, so what was there on my screen originally, just we're all out of order. Okay, does that look pretty close to what yours are? All right, I want to actually talk about how you sort of think about the tangent lines, because so far all I did was draw a couple of them, and I didn't really tell you what you were trying to do when you were drawing them. And so Jalissa's already got another sheet of paper out, and hopefully you have another sheet of paper close enough, or grab your ID card, back of your calculator lid, something that's got a strong enough edge you can draw along, okay? So grab something else to draw along the side of what you're doing right now real quick. This says to sketch a plausible tangent line. So when you do get to this question on your homework, what you're going to do is you're going to put your paper down on top of the graph and you're going to sketch it onto the paper to start with, okay? Put the dot on there and so forth. And then to sketch a plausible tangent line, it has to be a tangent line that looks very, very close to the curve as you are getting close to that point. So, oh, you know what? Green will work. Let's take a look here. So if I'm taking this green as my straight edge, I have lots of things. I might think that it's like this, or I might think that I'm doing like this. The goal is to take this right here and to get as close as possible on both sides of the dot and then to draw the line in there as straight as I can. Okay? That's the general idea for a plausible tangent line. Now, if you do that at the point B, or let me do the point A here. So at the point A, all right, that's pretty reasonable. I have this. Well, if you do this at the point B, what do you notice? It will cross the other one, that's true. But what do you notice about, ignore the other line that I've already drawn. Does it have to go down? It'll be flat. I've put it at the very top of the peak here because I want you to recognize that it actually could be a flat line. And it is if it's really at the peak or the valley of a graph. It really will be that way. The point C is an interesting one because if you draw this at the point C, this is one of those occasions where it really pretty close to crosses through the line, through the curve. Because in order for it to be tight over here and tight over here, that is tight on either side of the point C, you're going to have to be really close to that curve on both sides. And it's actually going to look very much like it crosses through the line, and we'll learn more about why that is later. So this one looks something like this. That's not a very good drawing. That's a little bit better. And then the last one from point D, and then we'll stop, looks something like this. Can you see that at all? No? Let's try a darker color. Okay, so these are plausible tangent lines. And we'll pick up back this point next time, and we'll talk about when we take a look at those lines, interpreting or listing the points in order of increasing slope.